Hey there, and welcome to today's Explainer. I've got to say, I'm genuinely pumped to dive into this with you. Today, we're tackling literally the mathematical backbone of modern communication systems. The title of our deep dive is Representation of Signals and Systems. You know, if you've ever stopped to wonder exactly how your smartphone, your Wi-Fi, or heck, even just a simple car radio actually manages to transmit all that incredibly complex information through thin air, well, the secret is hidden right here in the math we're going to explore today. We're taking those big, heavy theories from communication engineering and breaking them down into super clear, visual concepts.
So here's the roadmap for our journey today. First, we'll look at the two signal domains, then unpacking the spectrum. After that, shifting and scaling signals, followed by the mirror of duality. And finally, we'll wrap things up with the fundamental signal limit. Okay, let's dive into this.
Kicking things off with Section 1, the two signal domains, a tale of time and frequency.
So on one side of things, we have the time domain. Now, this is probably the one you're most familiar with, right? It shows how a signal changes literally second by second, or, millisecond by millisecond. It's kind of like reading a book or watching a movie unfold continuously in real time. But then, on the other side, we have the frequency domain. Instead of just looking at a timeline, the frequency domain shows us the specific recipe of frequencies that make up the whole signal, all at exactly the same time. Think of it this way. If the time domain is a fully baked cake, the frequency domain is the ingredient list. It shows you exactly how much sugar, how much flour, and how many eggs actually went into making it.
Now you're probably wondering, okay, how do we actually get from that baked cake back to the ingredient list? Well, the answer is the forward Fourier Transform. This elegant little equation is basically a magical mathematical bridge. It allows us to travel straight from the time domain right into the frequency domain. By taking the time signal, let's call it GFT, and integrating it over all time against a complex exponential, this equation essentially uncovers the specific frequency components hidden inside the signal. It's basically building the entire signal from scratch by adding up an infinite number of complex exponentials. Pretty wild, right?
Moving right along to Section 2, unpacking the spectrum, amplitude and phase.
Because the spectrum is a complex quantity, it actually breaks down into two distinct parts, magnitude and phase. To really wrap our heads around this, I want you to picture a vibrant, super animated orchestra. Like, imagine something straight out of a Pixar movie. The amplitude is basically the volume of each individual instrument. It tells us, say, exactly how loud the trumpets are playing compared to the violins. But listen, a great piece of music isn't just about how loud it is it? It's all about the timing, and that's the phase. Phase represents the exact timing and those precise entrance cues for every single instrument. I mean, think about it. If the phase is off, the trumpets come in 3 seconds late, and the whole song is a total disaster, even if the volume was absolutely perfect.
So, to put it formally, the amplitude spectrum represents the strength, or the energy distribution, of each frequency component. Meanwhile, the phase spectrum represents the time alignment, or the phase delay. The really crucial takeaway here is that both of these matter immensely. In fact, and this is a huge deal in engineering, phase is absolutely critical for modern systems. If you've got phase distortion, your high-speed digital communications simply will not work. The timing of the data packets will literally collide with each other.
All right, that brings us to Section 3, shifting and scaling signals, the rules of the realm.
First up here is time scaling. I always like to think of a signal as a thick rubber band. If you compress the signal in time, which means you speed it up so it finishes much faster, you literally have to stretch that rubber band out. And what happens to a rubber band when you stretch it? It gets wider, but it also gets thinner. In signal terms, when time is compressed, the spectrum expands, it gets wider. And conversely, if you expand the signal in time, like letting it play out really slowly, the rubber band relaxes and the spectrum compresses, becoming super narrow. This inverse relationship right here is absolutely fundamental. Compression in one domain strictly forces an expansion in the other domain.
Now let's talk about frequency shifting. By simply multiplying a baseband time signal by a complex exponential, the entire spectrum shifts so it's centered around a brand new carrier frequency. Let's look at a quick textbook example here to make this totally concrete. Say you have a baseband signal that spans from 0 to 10 kilohertz. If your complex exponential is set to, let's say, 1 megahertz, your entire spectrum perfectly slides all the way up to sit right at that 1 megahertz mark. The actual shape doesn't change, the amplitude doesn't change, it just simply slides right down the frequency axis.
So why does this matter? Well, because frequency shifting is literally the exact secret behind modern communication. This mathematical property right here is the formal proof for modulation.
When you get in your car and tune the radio to 99.5 FM, what you're actually doing is looking for a signal that has been intentionally frequency shifted to be centered at exactly 99.5 megahertz. Without this specific property, oh man, every single radio station, every Wi-Fi router, every cell phone would all be broadcasting over the exact same baseband frequencies. It would just create this massive, completely unreadable wall of noise, total chaos.
Okay, moving on to Section 4, the mirror of duality, rectangular and sync pulses.
Check out this side-by-side comparison. Over on the left, we've got an RF pulse in the time domain. As you can see, it looks like a really high-frequency cosine wave, and it's perfectly neatly packaged inside a finite rectangular window of time. We'll call that capital T. Now look over on the right at its amplitude spectrum in the frequency domain. It looks completely different, right? It's split into two distinct shapes that are centered at the positive and negative carrier frequencies, and the shape itself has this large main lobe with these little rippling side lobes trailing off. I just love this because it brilliantly illustrates how a really sharp, sudden start and stop in the time domain actually creates these literal ripples of energy that just spread out across the frequency domain.
So let's see how this builds into the formal concept of duality. A rigid rectangular shape in the time domain naturally transforms into that rippling shape, which we call a sync function in the frequency domain. But because of duality, if we actually swap their roles, like if we force a signal to have a perfectly rectangular spectrum, which is basically an ideal low-pass filter in our textbook examples, then its time domain waveform absolutely must become a sync function. The Fourier transform essentially just gives you the mirror image. Rectangular pulse gives a sync spectrum. A sync pulse gives a rectangular spectrum. It is just this perfect, totally unbreakable mathematical mirror.
And that leads us right into our final section, Section 5, the fundamental signal limit, the inverse relationship.
I really want this fundamental rule to sink in for a second. A signal cannot be strictly limited in both time and frequency. In practical engineering terms, this means a signal simply cannot be narrow in both domains at the exact same time. You always have to make a trade-off.
Let's try to visualize this trade-off. If a signal is strictly limited in time, meaning it starts at 0, it turns on for just a brief, tiny moment, and then goes perfectly back to 0, its spectrum absolutely must spill out infinitely into the frequency domain. Imagine you've got this tiny, finite animation box, right? But the second you open it, this endless, infinite array of colors just bursts out everywhere. The sharper and shorter your time pulse is, the wider and more infinite its frequency footprint becomes. And, of course, conversely, if you strictly limit a signal's frequency band, its time domain waveform is going to trail on endlessly. It'll never fully reach 0.
We can actually quantify this exact physical limitation with this incredibly elegant equation right here, the time bandwidth product. It states that the duration of a signal multiplied by its bandwidth will always equal a constant. Let's look at another classic textbook example. Let's say a rectangular pulse has the duration t of exactly 1 millisecond. Well, its null-to-null bandwidth is 1 over t, which gives us 1 kilohertz. If you take that pulse and compress it down to half a millisecond, mathematically the bandwidth has to double to 2 kilohertz. There's just no way around it. You can never shrink both. You squeeze one side and the other side bulges right out. This one single product actually dictates exactly how fast we can send data through a communication channel without all the signals just bleeding into one another. So up to this point, basically everything we've discussed regarding the Fourier transform really relies on the signal having finite energy, which just means the signal eventually ends. But what about signals that never end? What about a pure continuous DC current or an endless sine wave? I mean, these are infinite power signals, and frankly, the standard Fourier transform math actually breaks down when we try to analyze them. So how on earth do we bridge that gap? Well, the answer lies in this really fascinating, rule-breaking mathematical concept known as the Dirac delta function. But as for how that completely upends our whole tool set, well, I think that's a brilliant question to leave you with, and honestly, it's the perfect place to start our next exploration into communication engineering. Thank you so much for joining me on today's Explainer, and hey, keep questioning the signals around you.